Hello everyone. We are continuing our additional material in the software architecture class where we discuss about secure software engineering besides just good software design and architecture. I would like to mention here that this material, even though it's outside of the book, will be included in your final exam. And this week, we're going to be reviewing how we as developers handle sensitive data and how we can secure it for its confidentiality and integrity. By defining what is sensitive data, and then we will continue reviewing two techniques that are used to secure data. One is called hashing, and the other one is encryption. So it is important for a developer to know what exactly is sensitive data, and that's why I'm getting into this detail of defining it. We have discussed before the pillars of security: CIA, confidentiality, integrity, and availability. So with data, the main thing we want to do is keep it confidential, keep it private, keep it solid and correct. That's the part of integrity. And then, of course, keep it available, because if we need it, we need to be able to access it. And we define sensitive data as personal information, such as your social security number, even your date of birth and other things, your address and all that. Some of this is public, but still, in combination, it could be destructive to lose it, because somebody could impersonate you. Then we define sensitive data as the health information. So many times health organizations are target of data breaches because they have this sensitive data that can cause, and they may have, there may be different reasons that somebody wants to compromise these for profit, for nation controversies and things like that. So in the United States, we have the Health Insurance Portability and Accountability Act, or HIPAA, that is an act to define and specify the rules on how we have to protect this data, and all the health organizations have to abide by this by the HIPAA Act. Then in academia, we have FERPA, the Family Education Rights and Privacy Act, where it defines the privacy of a student and how we need to handle their grades confidentially. So as an academic organization, we have this mandate, and we also do training, as they do in health organizations, for this specific act, FERPA. Then financial organizations also handle sensitive data, and this financial data is controlled by payment card industry, PCI, and Graham Leach Bliley, I'm not saying the GLBA Act. So customer records and cardholder records, very sensitive type of data, lots of data breaches, because that can be directly gaining money to an adversary. And of course, very important to keep this type of data protected as developers. Finally, there is HR that needs to keep our data protected, and then there's the State Personnel Act that defines these, and in general, information that is deemed to be confidential, such as the intellectual property of an organization or the intellectual property of a federal government. These types of things are sensitive data that we want to keep secret, and we as developers may be called to protect it with our software products. So how do we protect this kind of data? Well, you have probably used many times the a password in order to authenticate yourself. So passwords are ways to protect our applications from anyone accessing the data that we're handling. So let's say if you were making a healthcare organization software application, you would have passwords so that you can authenticate doctors and that they were the only ones that can access patient data. If you were making an LMS, a learning management system that is OAKS, that I am using for your grades, you would be using passwords to authenticate professors, and you would have different access controls for professors versus students. So passwords are a good way of making sure that people that should be accessing the data are the ones that say they are. However, there are issues with passwords. You may have had to handle a few hundreds of passwords for the different websites that you use. So even though you try to make these as random as possible, as difficult as possible to guess, it's very difficult to remember those. So that's why a good practice as a user is to use a password manager. As a developer, you may make your users use more complicated passwords by making rules in your software app. However, this may irritate your user because usability is getting hurt by these kinds of things. So users also may disclose their passwords, and that defeats the purpose of having a password, because then multiple people may authenticate on the same account when they're not the same person. And then, of course, your applications may revoke a password because your user tried too many times and they did not use the right password, which can be bad for usability again, how do they retrieve it, and things like that. And of course, passwords can also be lost. People may forget them and all that. So there are, unfortunately, issues. However, it's good to use passwords and handle them properly, especially when you're handling sensitive data like the ones that I mentioned before, financial data, health data, which is quite likely to be doing these kinds of things with the software products that you will be creating in your career. I have a list of rules that you could use in your software application to create stronger passwords. So I use these. This is a standard. I use this in my security class to teach students that want to be security analysts on how to make their users create stronger passwords, but they can be used by a developer as well, as I'm saying in this software architecture class, to force the user to create stronger passwords. Like, for example, if you detect that a user is using just an English dictionary word, and it's very easy to guess the password, and you can even have more sophisticated algorithms to guess, to compare the password against the dictionary and all that, then you can tell the user you need to use special characters, you need to use capitalization and other things that will make the password include more information, include more randomness, and make it more difficult to attack. A fun picture that I like to show, a professor from Carnegie Mellon University that is working on research in usable security, and in her sabbatical she did some quilting, and she made the password dress, which is truly taken from her research in people's passwords. She did some research in looking at the most common passwords that people use, and found all of these and made this word graph. And it's very interesting because still, if you Google around, you will see that people keep using these very common passwords, and there are lists of common passwords all around in open public websites that, of course, developers can look and think, how can I make my user pick better passwords? But also adversaries can look and say, oh, let me brute force the passwords in this website by using all these common passwords because they're still very much used. So a double-edged sword to have this information publicly. However, with good information, being informative, we can help our users and via our software applications to secure their accounts and their private sensitive data. So in case you're taking my security class, we have talked ad nauseum about how to handle passwords as security analysts, of course, but now as developers, and some of you may not take that class, so it's very good to mention this because every developer should know these techniques. So how you should not store passwords, and many of your applications will be handling passwords. So I have no doubt about that. So never store a password just in plain text. So let's have a file or a database that has our passwords and store them in plain text. Big no-no, because your adversary may compromise the database and then you've given them a free pass with your plain text stored passwords. The other thing that is even confused by good, knowledgeable security people is you cannot store the passwords encrypted because encryption was made to be reversible. Encryption is like locking a secret into a box and you have a key. And if somebody gets the key, it can unlock the box and get all the secrets. So it's almost as good as plain text if somebody has the key. Of course, if it's strong encryption, it's tough to guess the key, but the key can compromise everything. Okay, so encrypting passwords is not as good a good idea. It also defeats the purpose. Your database and you don't need to know what your user password is. So you don't need to reverse the data and get the plain text, the actual password data. So the best way to store passwords is hashing, but not just hashing. Hashing is an irreversible encryption. You can think about it as an encryption algorithm, but it's irreversible. So you can only do it one way. You can only scramble the text and make it unrecognizable, and you cannot reverse it. So every time your user types their password, all you do is rehash that password, compare it to the hashed version that you have in your database, and then your user is good to authenticate. But because hashing is, even with the computational abilities that we have, can be brute forced, especially if users are using these common passwords and all that, it can still be brute forced, even though it's not reversible. We add some additional randomization to the passwords. We call this a salt, which is we add some additional information like a random number or some random set of digits in order to salt and hash the password and make it even more secure. And this is the standard way of storing passwords. Salting them, sprinkling them with salt, something random, a random number, and then hashing them. And this way, you even save the users that do not want to abide by your randomization rules. So let's say you have two users that saved their passwords, and their passwords are password 123, a super common password that could pass through all your rules because it's using, let's say, capital and maybe a special character and some numbers. You still save those users by randomizing even a little further their passwords. And when you salt, you save the salts in a separate database. So if one database gets compromised, the other one does not, or it's small likelihood to get all your databases compromised. That's got to be a pretty bad day. And then again, you make the adversaries work more difficult because even though they may be able to brute force the hashes, if they don't have the salts, they're going to have even a harder time. So really good things to think about. As a developer, you don't need to know all the details of an encryption algorithm or a hashing algorithm. You just need to know the standard ways of handling passwords and data in general. So, and that's why, and I'm saying this already, in this class, I don't get into all the details of these algorithms. You can take a security class to understand those more, and maybe as a security analyst, you will improve upon those. But as a developer, you will only use those. So as I said in the previous slide, I'm not going to get into the details of the math and algorithmic details of hashing and encrypting. All you need to know about hash functions is that they are one-way functions. They can lock your secrets, but you cannot unlock these. You can only compare a hash to a hash and then authenticate your users. And then this way, nobody can get the plain text of your user's password. And the other thing you need to know as a developer is that every high-level language, Python, Java, C# implement the standard strong hash functions, and you can use those to secure your passwords when you're saving them in your database. So that's a nice picture that explains a little bit more how hashing works. So the hash function takes a word and makes it, as you can see, completely unrecognizable. There is no rhyme or anything that you can use to reverse this. And that's why this is the standard way of storing a password into a database. And the only way that somebody can guess that password is if they rehash the word hello, compare it with the hash that they found in your database, and then if they see it's the same, then the password is hello. So you can see that the only way that this can be done is by completely brute forcing, using a dictionary or all the possible combinations that the password could get. And of course, the more random and unusual the password is, the more time it's going to take to brute force it. And that's the protection of our passwords right now, because unfortunately, many passwords databases get compromised. As I said, many password databases get compromised and there are password attacks. I will say here that we even hear about password databases that they get compromised and they don't give any rough time to the adversaries because they are in plain text. So don't be that developer that stores their passwords on plain text, and be the one that stores the passwords properly with proper randomization results and proper hashing, which is ready to go library in your Java or Python API or whatever language you prefer to use. The password attacks that can be used, even if you do your work right, are of course guessing, because your users may still be using a very common password. Dictionary type of attacks, take a dictionary, hash it, compare it to the hashes that you found, and then eventually you may find some overlapping, so now you have passwords. Or rainbow tables, which are pre-salted dictionary tables that help when you even do your job perfectly, like you even solved your passwords. There may be rainbow tables, pre-salted, pre-hashed tables to make the computation a little faster for the adversaries. Still, if you do your job right, if you use the standard libraries with strong hashing algorithms and you add some randomization with salt, nobody's going to blame you for, not doing your job right. So there's that. But you will also truly defend your users' passwords. So use strong hashing algorithms, and that is the way to go. Again, another good visual to show how passwords can be attacked through these brute force attacks. And there's even tools that people can use. They don't even have to write custom code to crack passwords. Again, these I teach in more detail in the computer and network security class, but it's good to know that there's standard tools that can break your passwords, so use the proper techniques. Detail about salts and peppers that are used to randomize our passwords. And here are some ideas on how to create a salt, for example. Again, as a developer, you may have to do that. You could use the date that the password was created together with the timestamp. You could take that with system time. You could use the username of your user to create a salt, or you could use something random, a random number generator, for example. Pepper is just an additional randomization, but all I'm going to say is that if you decide to, let's say, use passwords which in your project they don't make that much sense because you have to handle a very small Fitbit screen, but in the software architecture project that I give on election years, I ask for an election software, and there they handle passwords. You would need to use either the username or a random number to salt your passwords, and then of course use a standardized library to hash them. In conclusion, to protect our user authentication, we can make better passwords through our software, make our users use more randomized passwords and all these good things, use hash and salt and maybe pepper if we want to be even more secure to randomize our users' passwords. And finally, use a strong hashing algorithm. As I said, there are libraries, you don't have to implement these things from scratch. And the algorithm that you shouldn't use, even though it still exists in the libraries, is MD5. It's a weak hashing algorithm that can be broken easily. You need to use the SHA standard algorithms, and the higher the number, the higher the length of the hashing that you create, like 256, 384, 512. 512 is the best, but of course for performance you may have to weigh these two things. Whatever you do, do not use MD5. And that's all a developer needs to know. Now, again, if you want to get deeper into these algorithms, definitely a security class will get you there. Now, this is a fun activity that I do in class. It's very easy coding, actually, and I would encourage you to try this. It's really easy, and you can stop the video and try this code that I have on Oaks in the class activities, and try to fill the code. It's super easy to fill it. Actually, it's almost like copy pasting chunks of code. And of course, ask me on Slack if you have any questions, because this is nice at this point to stop and maybe try these things again as a developer and look at the actual differences between hashes. I will say that even though this project does not have much secure data handling, if you learn these things, if you do this little practice and all that, that will probably take you 10, 15, maximum 20 minutes. You will become better developers, and you will definitely make a difference in the world with your code being more robust and more sophisticated, because we can make a difference as computer scientists and change the security landscape. And it starts from us, and it starts from us teaching you guys. So strongly encourage you to look at these examples, even though you don't do the whole activity. Just look at the code and then run it and see what it looks like. Now, as developers, we may not only need to authenticate our users using passwords and handle their passwords securely, we may also need to transfer data via an unsecure medium, the internet, and even be able to read this data, such as write an e-commerce application that takes credit cards and uses them to help the users buy different things. So in this case, we will need to use encryption, which can secure our data and guarantee the confidentiality of our data. But with the key, with us having the key and our users having the key, we will be able to retrieve the data and use it for a transaction or any other type of activity that we need to use this data for. And here I will give just the 10,000 foot view of cryptography, and I'm not going to get into the details of the algorithms. A security class is appropriate for that. And so we have two types of cryptography: secret key cryptography and public key cryptography. In this slide, I'm showing the secret key cryptography, which is, the analogy would be that Alice and Bob want to exchange credit cards. Alice wants to buy something from Bob, so she wants to send her credit card. So the first thing they do is they need to share a common key. That's what we use in a secret key cryptography, a common key, a single key. And then Alice will use that key to lock the message in a box or encrypt it. And then Bob will use the same key to unlock the box, get the message, or decrypt it, as we say in the terms of encryption. Eve may be eavesdropping an unsecure medium, such as the internet, which anybody can eavesdrop. But if she doesn't have the key with the very strong secret key cryptography algorithms that we have nowadays that are implemented in every higher level language libraries, Eve is helpless without the key. She cannot break the crypto, whatever she tries, brute force, blah, blah, blah. She's helpless. So that's secret key cryptography. It's much more efficient than public key cryptography, much less calculations, smaller numbers that need to be used for the keys. However, there is a caveat, and the caveat is that Alice and Bob need to share a key over an unsecure medium. And for this, they use public key cryptography, where they don't need to share anything. And then after that, they use the efficient secret key cryptography for the rest of their transactions. So in the next slide, I will explain public key crypto and how we exchange keys with that. And then we use those keys to do the more efficient, faster crypto. Here I'm going to give a 10,000 foot view of public key cryptography. And in this case, Alice and Bob have a pair of keys, personal keys. Alice has her own private key that she never shares with anyone, and her own public key that the whole world knows, even Eve, the eavesdropper. On the other hand, Bob has his own private key and his public key. The private key never is shared anywhere. The public key is given to the whole world. And how asymmetric crypto or public key crypto works is this. Everyone should be able to encrypt, but only the person that is addressed to should be able to decrypt the message. So when Alice wants to communicate with Bob, she knows Bob's public key. She should be able to encrypt the message with his public key because the whole world knows it. And then she sent this message to Bob, but even if Eve eavesdrop it, only Bob can decrypt that message because only Bob has his private key that can unlock that message. And it's a little bit magical the way public key crypto works. It works based on the properties of prime numbers, moduli, and power, type of mathematical functions. I'm not getting into the details, but it truly works. Anybody can encrypt the message with Bob's public key. However, only Bob can decrypt this message that is addressed to him. And therefore, even though the public key is known and shared everywhere, the eavesdropper cannot break that crypto. So this is a way that we share keys. So Alice may send her key this way to Bob and say, this is my secret key. And after that, let's use more efficient secret key crypto. And they use the more efficient secret key crypto for multiple transactions. So this is exactly what happens when you visit a secure website like Amazon to do your purchases. With public key crypto, your private key is sent to Amazon, and only Amazon can decrypt that key. And then after that, all the back and forth for the transaction, like your shopping cart, your credit card, more shopping, happens with this secret key crypto. So this is the 10,000 view of cryptography, 10,000 foot view of cryptography. I kept some additional slides in your slide deck, just in case you're interested in looking at the details. Again, I welcome you to look into more resources, taking these additional security classes and all that. But at the end, I'm going to just review, in the next few slides, I'm going to just review the implementation of these crypto algorithms in Java, which is the language that we use in this software architecture class. So this is a little bit reviewing the Java Crypto Cipher library. You can find this code in the links that I have in the slides and run it for yourself to see what it looks like. Essentially, the biggest thing that you need to understand about crypto algorithms is that they work on bytes, not the standard characters that you have seen. So you have to transform, let's say, the credit card number that you're handling with your software to bytes, encrypt it, then decrypt it, and then transform the bytes to strings to actually use them in your code. It's very, very easy to substitute different algorithms by substituting DES with more secure algorithms. The strongest algorithm that we are actually using currently is the AES, the Advanced Encryption Standard. DES is a weak encryption algorithm, so we don't use it anymore. And so this is very worth doing a little practice, getting these libraries and using them. And I have a little more code that I'm going to discuss in the next slide. So after you manipulate your data, and let's say the credit card that is just a string of digits, you convert it to bytes, then you can, and you initialize your libraries appropriately to use the proper algorithm, not DES, but AES, the Advanced Encryption Standard. Then you can use the cipher, the crypto cipher library to encrypt by just setting some parameters into encrypt mode. And then, as I said before, this generates bytes. And then you need to manipulate your bytes to get your final cipher. And then after you have a cipher, you can decrypt it. Of course, if you have the key only, you can brute force the key. These are very strong algorithms. And all you need to do is then reconvert the bytes to characters and use them for the rest of your application. So definitely look at the Stack Overflow article that I have over there, and I would try to run this code on my personal computer. Again, excellent practice and making you a much better developer. So I have a last activity on the next slide that should take you 15 to 20 minutes maximum to complete, or maybe less. So very much worth trying this and seeing how encryption works.